and welcome to today's lesson. Today we're going to look at what are called trigonometric identities. And to do that, I'm going to start off by going back to the x and the y axis and drawing, I'm going to draw the following. I'm going to take a length of 1 and swing it up to about there. Okay, so this is 1 unit. What I'm now going to do is construct a little right triangle here as follows. Okay. And for this end point on the terminal arm, it's going to have a length, well, the point's going to have coordinates x and y, and what that gives us is the length of the legs of the right triangle. So this length here, the distance we've moved to the right, would be x, and then the length that we've moved up to get to that point is y. And this would be our angle theta down here. Now, based on this sketch, I'm going to develop what we will be calling some of the trig identities. And the first ones that I'm going to develop are actually pretty interesting ones. They're going to be based on the following trig functions that we just get from the triangle itself. And so I'm just going to list those here. Sine theta, according to our triangle, would be opposite over hypotenuse. So that would be y over 1, or just y. Cosine of theta would be adjacent over hypotenuse, or x over 1, which is just x. And tangent of theta would equal y over x, opposite over adjacent. Now, I'm also going to list the reciprocals, which are the cosecant of theta. Cosecant is the opposite of opposite over hypotenuse. Okay, so instead of 1 over y, it's y over 1. The secant of theta, instead of x over 1, is 1 over x. And cotangent of theta is the reciprocal of y over x, so x over y. And so some very simple identities we can develop are called the reciprocal identities. So that's the first family of identities that we're going to look at. The reciprocal identities are very simple, and the name kind of says it all. Sine theta is the reciprocal of cosecant theta. And so what does that mean? Well, it means that we believe sine theta is equal to 1 over cosecant. In other words, the reciprocal of sine, which is cosecant, so sine should equal the reciprocal of the reciprocal. It's all very, very mind-boggling in a sense. But let me see if I can prove this to you. And this would be one of our very first looks at a trigonometric proof. Now, space is going to be compacted here. So I think now that we've got our drawing, I'm going to erase this and try to keep these identities here. So let's see if that will work. We have sufficient room to prove this. Well, let's have a look at what sine theta looks like. Sine theta is y. Okay? And so I'm going to replace the left side with y. And the right side is 1 over cosecant. So that says 1 over, and cosecant theta is 1 over y. So I'm going to replace the cosecant with 1 over y. We're trying to prove that y is equal to this. Well, a little bit of simplification on the right. I think what I'm going to do is multiply the top and bottom here by y, and that will get rid of the fraction. So what does the right side look like? 1 times y over 1 over y times y. The y's cancel. It's over 1, and my goodness, I have y equal to y. So since we started with sine theta equals 1 over cosecant theta, and we have indeed shown that when we analyze these, we get the same thing on the right side and the left side. That proves this first identity. So let me just list some of the other relationships, and I won't be going through an extensive proof, but let me show you what they would look like. So, with a little bit more space here, what do we have? Well, we have sine theta equal to 1 over cosecant theta, and so that means we also have cosecant theta equal to 1 over sine theta. Makes sense. You can reciprocate one side or the other, and they should be the same. Similarly, we have cosine theta equaling 1 over secant theta, or its kind of other version is that secant theta equals 1 over cosine theta. And then, of course, we have tangent theta equaling 1 over cotangent, and cotangent theta equaling 1 over tangent. So these are the reciprocal identities, most of which seem to follow a certain common sense. Okay, so that's the family of reciprocal identities. Now let me see if I can show you another family of what really are some of the more useful of the identities. These ones are incredibly versatile. We use them a lot, and they're called the Pythagorean identities. So named after good old Pythagoras. Pythagorean identities. Okay, what are these things going to look like? Well, they're rather an interesting thing. You'll recall that when I had our triangle, I'll do kind of a mini version here in only the one quadrant, we had something like this. There was our right angle, there was theta, this was x, that was y, and that was 1. Well, Pythagoras' theorem gives us a kind of nice relationship here. X squared plus y squared equals 1. What has that got to do with trig, you might be asking? Well, if you recall, of course I erased it due to limited space, but if you recall, the cosine of theta was the same thing as x over 1, or the same thing as x, and the sine of theta was the same thing as y over 1, or just y. So now I can go here and say, well, x, y, heck, let's put some trig functions in there, square them up, and we'll switch the order because we kind of like sine before cos. I don't know why. It just looks nicer, I guess. But this is how we write it. Sine squared theta plus cos squared theta equals 1. You'll notice we put, immediately after sine, we put the little squared. This actually does mean the same thing as sine theta all squared. The reason we write it this way is the brackets seem to be an extra amount of writing that most mathematicians don't want to do. And if you drop the brackets, then it looks like you're taking the sine of theta squared. And that's not the case. We want sine theta times itself. So the traditional way to write it is to put the squared right after the trig function. So this would be what the actual meaning is. Well, that's a pretty handy identity. And sometimes we use different versions of it where we'll say, oh, that tells us that cos squared is the same thing as 1 minus sine squared theta. That kind of thing can sometimes be very useful. So we do some rearrangements of it. So this is kind of the first of the Pythagorean identities, and I like to refer to this as my favorite all-time identity. It just seems to be really handy. Pretty practical stuff. So let me just show you some of the other Pythagorean identities and where they might come from. Let's take sine squared plus cos squared equals 1, and backtrack that back to the x and the y form. Okay, so just erase this. Let's start off with x squared plus y squared equals 1, and then for some crazy reason, I'm going to divide everything by x squared. So if I divide everything by x squared, what am I going to get? Well, x squared divided by x squared is 1. And then I have y squared over x squared. What is y over x? Well, let's go to our little triangle here, and y over x looks an awful lot like tangent. So this is really tangent squared theta. Okay, y over x, tangent theta, and we're squaring it. And then we have 1 over x, also squared. You can think of the 1 here as squared if you like, so you can think of it as 1 over x all squared. Well, I know that x over 1 would be cosine, and so 1 over x must be the reciprocal, or secant. So this is equal to secant squared theta. Okay, and I'm just looking at these relationships with x and y and 1 over x and saying, well, what is that in trig lingo? And that's what it is. So there's another identity. Another of the Pythagorean identities. Not quite as useful as sine squared plus cos squared equals 1, but glorious in its own way. Now, there's one more of the Pythagorean identities that we can glean from this triangle. Let's just go back to our x squared plus y squared equals 1, or 1 squared if you like. And we're going to do the following. We're going to now divide everything not by x squared, but, and I hear you saying it, y squared. So now what do we have? Well, let's see. We got x over y all squared, if you like. X over y, that would be the reciprocal of tangent, so that would be cotangent squared. Y over y, that's just 1. And then I got 1 over y. Well, let's see, that's sine would be y over 1, so 1 over y, the reciprocal, that would be a cosecant of theta squared. And there it is, just sort of shows up out of thin air almost. It's another Pythagorean identity. So those are the 3 Pythagorean identities. And then we have another family of identities we need to look at. They're called the Quotient Identities. So I guess we can clear this away. I'm going to leave the triangle this time. Sometimes it's handy to have that triangle in front of us. Well, it's always handy, actually, to have the triangle in front. Anyway, these are the quotient identities. And you'll like the fact there's only 2 of them. Okay, so what could they be? Well, quotient means we're dividing stuff. So let me see what I might be dividing here. What if I took something like this? What if I took, for some crazy reason, what if I wanted to see sine theta divided by cos theta, and I wondered, what does that look like? What is that? Well, let's have a little look. Sine theta, well, that's y over 1, which is just y. Cos theta, well, that's x over 1, which is just x. And then I look at this and I go, what, y over x? Could be wrong, but I think we're talking about tangent here. Tan theta, so there it is. We don't really need the middleman here, so I'm just going to make them go away. There it is. Sine theta over cos theta equals tan theta. And of course I could just flip things over here. Cos over sine. What do you think that might be? The flip-flop of tangent. Of course it is cotangent theta. Those are the quotient identities. So that's the first family of identities that we're going to look at. And I think what we'll try and do here is kind of show you one purpose of why we have these identities in the first place. Why might we have all these sort of swaps and switcheroos and changes? Well, they're very useful in proving things. And proving what? Well, proving, for example, let's see if we can think of a good one here. Just hold on while I find something that might be good to try to prove. Let's see if we can prove that. This looks like a really tough one here. We're going to try and prove this. Hope I can fit it all on the board. That cos squared theta all over 1 plus 2 sine theta minus 3 sine squared theta. Oh boy, that's pretty ugly stuff. That might equal 1 plus sine theta all over 1 plus 3 times sine theta. So that's got to be as ugly as they get. Okay. Now we're going to try and prove that the left side and the right side are saying the same thing. So I'm going to use a little trick here, and sometimes there's simple identity switches, and sometimes there's tough ones. But I'm going to use a little trick here. I'm going to look at this thing here and say, well, that looks an awful lot like a quadratic equation. I've got kind of a something squared, and I got kind of that something, and then a number. So I'm thinking that just might factor. So I'm going to try factoring it. And of course, you guessed it, it's cooked up so it factors. So that's going to be my strategy here. Now I'm just going to cram this in here and ask myself, to get the number 1, I would go 1 times 1. So that's pretty limited choices there. Now how do I get negative 3 sine squared? Well, pretty limited choices there too. I'm going to need to have a sine theta times a sine theta. And one of these has to have a 3 in front. So it'd be like 3 sine theta times sine theta. But to make it negative, one of them has to be negative, then the other one has to be positive. And I want them to add up to positive 2. So I want the 3 to be the positive number, and the 1 sine theta to be negative. So that's the factored version of that, believe it or not. Now here's where the identity stuff kicks in. Remember our favorite all-time identity, sine squared plus cos squared equals 1. And I showed you a little rearrangement of that that said, you know, cos squared, that's the same thing as 1 minus sine squared. Okay, so I'm going to go ahead and put that in there. I'm going to make that swap. It's using the identity. And then I'd look at this for a little while, and suddenly I'd go, okay, I think I see a way through the jungle. Believe it or not, this also factors. Perhaps somewhere in the old days you remember factoring a difference of squares. If we think of 1 as 1 squared, then we have something squared minus something squared. That factors as a difference of squares, and it would look like this. 1 plus sine theta times 1 minus sine theta. And if you ever have doubts about your factoring, you can always expand out the brackets and make sure you do indeed still have 1 minus sine squared theta. On the bottom, I still have 1 plus 3 sine theta times 1 minus sine theta. Well, I think you can see what's going to cancel. 1 minus sine theta cancels with 1 minus sine theta. And look what I have. I have 1 plus sine theta over 1 plus 3 sine theta. That's exactly what I have on the right. And what we usually say is left side equals right side. Yippee, I've proven it. Okay? Now, just while we're on the topic, since we've seen a pretty miserable proof here, what are some of the do's and don'ts, and what are some of the tricks that might help you with other proofs that you're working on? Well, some of the do's and don'ts. What we usually do is this. When we work on a proof, we kind of put a little line down the middle. And what that means is you work the left side and the right side independently. You try to avoid things like cross-multiplying. Those are kind of considered no-nos. You just work them independently and you try to get one side to look like the other side. Some of the other tricks of the trade, if you have things like tangents showing up or cotangents, what we like to do is put everything in terms of sine and cosine, and usually that causes things to start to cancel. So I always try to put all terms into sine and cos. There we go. That's a really handy trick. There's another trick which didn't come up in this example, but I'll show you with another example, and that's using something we call the conjugate. When nothing else works, that's when I think to try the conjugate. I'm going to show you an example of how we can make something look quite different by using the conjugate. The other trick that is very useful in these proofs, and that is to combine fractions. And I'm going to show you an example of that as well. Now, these aren't going to be lengthy proofs. I'm just going to quickly show you what a conjugate and what a combining fraction is, what I'm talking about there. So let me do that up here with a quick, simple example of some sort of a conjugate. What might we be talking about there? Well, let's say I had to work with something like this. Maybe I had 1 minus sine x, and on the bottom I had, say, a cos x. So I was going to try and make this look differently or something. And I'm thinking, well, what can I do with this? The conjugate would be to multiply the top and bottom by this two-termed expression and changing the sign from minus to plus. Okay. Now, if this was a plus, then this would be a minus, top and bottom. So how does that make this thing look different? Well, let's see. 1 minus 1 would be 1. Then we'd have positive sine x, but we'd also get a negative sine x, so those would cancel. And finally, we'd have minus sine squared x. And as for the bottom, I'm not even going to try to expand that out. Actually, I have my reasons not to expand it out, which might be clear in the next step. 1 minus sine squared x. I think I've seen that before, and I think that that's cos squared x. So now I've got cos squared x over cos x times 1 plus sine x. And what does that look like? Well, I can cancel one of these cosines with a cosine on the bottom, and that would simplify down to cos x over 1 plus sine x. So in fact, what we've shown is that our original expression, which was this, 1 minus sine x over cos, is in fact the same thing as cos x over 1 plus sine x. And that was using the conjugate. Okay. Now what about this combined fractions business? Well, let me show you what that would mean. Sometimes you get some weird looking thing and you have to combine it into one fraction. So you might get something like this. Say a 1 plus 1 over cos x. And you're going, well, if only I could combine these, maybe things could cancel and whatnot. So what you do is you take the number 1 and you write it as cos x over cos x. Now, anytime you get the same thing on the top and bottom, you've got the number 1, with the exception of 0 over 0, which is undefined. So I've rewritten the number 1 And I still have 1 over cos x over here. Then I could combine them. So my numerator is cos plus 1 all over cos x. Now, whether this is of great use to us in the context of some kind of trig proof, well, that would remain to be seen. But that would be, in some cases, a very useful maneuver. And with that, I think I'm going to stop for now on this topic of trig identities and trig proofs. So we'll catch you later.